I'm Nate Morrical. I'm a graduate student from the University of Utah and a member of the Scientific Computing and Imaging Institute. Today, I'm excited to present our work titled Attribute-Aware Radial Basis Functions, which allows you to interactively explore color-attributed time series particle volumes on a single consumer graphics card. But first, you might be wondering, why use particles for volume rendering? Well, as volume rendering improves, I think we're starting to ask ourselves the really big questions. In a world where volume rendering is a solved problem, then what's still holding us back? And in my opinion, we still seem to be struggling with spatial manipulation tasks. When we think of volume rendering, we often think of voxel grids, which are really easy to query and render, and there's tooling widely available for them. However, with grids, features are implicit, and so moving them requires some sort of segmentation, which is usually hard to compute. You might also consider finite elements, which have continuous vertex locations that allow these elements to twist and bend. However, manipulated elements must maintain a positive volume, otherwise they need to be remeshed. Compared to these prior formats, particle volumes robustly handle arbitrary motion, largely because they don't have connectivity data. And in my opinion, particles are also a better fit for what volumes really are, specks of material embedded in three-dimensional space. So then why aren't we using them? Well, when you think of particle rendering, you probably think of particle splatting. These methods transform particles and rasterize them onto the screen. However, if particles are colored, then compositing requires a sort from front to back, which becomes prohibitively expensive as datasets grow larger. Splatting also results in overdraw, which slows down rasterization performance. Visual artifacts occur when particles overlap, and because of that rasterization approach, it's really difficult to incorporate advanced lighting models. Ultimately, sorting and compositing particles just doesn't scale well to big data. So instead, modern splatters render density fields using additive compositing. This additive compositing is faster because it's commutative, and therefore it doesn't require any sorting. The thing is, other volumetric formats don't work that way. Grids store attributes in cells, while elements store attributes in cell centers or on the vertices. Then, we color map and composite these values using ray marching. For particle formats to succeed, we ultimately need to support both compositing strategies. Another approach to rendering particles is to rasterize them into a regular grid and then employ voxel-based ray marching. With this approach, you no longer need to sort colored particles, and it's much easier to support volumetric shadows. This is really just splatting in 3D instead of 2D, and similar limitations apply. Coarse grids miss fine details, while fine grids waste memory, and ultimately you must re-rasterize these grids when particles move. What we really want are direct world space queries that can utilize the full flexibility of particle formats. What we need is an approach that matches the behavior of other particle formats to enable high-quality, interactive visualization. So how can we query particles directly? The answer is radial basis functions. So radial basis functions describe a radial falloff about an origin and are typically denoted with a lowercase phi. A common radial basis function to use is a normal distribution. On the left is a one-dimensional illustration of a radial basis function where height represents density. On the right is a two-dimensional top-down view of that same radial basis function, where the value of the radial basis function determines optical density. From here, prior methods color map these radial basis functions by that same density value. Our radial basis function is parameterized on three values. The first is particle radius, which controls how small or large the particle is. The second parameter is weight, which controls how transparent or opaque that particle is. And the third parameter is a distance relative to the origin, which allows us to place our particles into the world. So with this single function, we can express quite a few things. In practice, we have multiple particles, and so it's convenient to replace that distance parameter d with the distance from the particle's center to the query origin. Then, we add multiple radial basis functions together to reconstruct our volumetric field. Individual radial basis functions are denoted with a lowercase phi, while their sum is represented with an uppercase phi. Let's say that we have three particles, v1, v2, and v3. Their sum is visualized on the left with a rainbow color map, and on the right as particles in our two-dimensional plot. When we increase the radii of our particles, they blend together in a behavior that almost looks like a lava lamp. And when we decrease their radii, they become distinct particles. The weight parameter can be used to hide or show different particles during exploration, and the distance parameter allows us to place particles into the world and to animate them over time. Now, we're not the only one to use radial basis functions for particle visualization. However, previous radial basis function visualizations typically only render density fields. I kind of think this is because assumptions were inherited from particle splatting, which were that color-attributed particles require expensive sorting. However, we're no longer constrained to rasterization, and so we can easily handle both of these cases through ray marching or woodcock tracking. So to extend radial basis functions to support color-attributed particles, we let theta denote an attribute associated with a particle. Then we compute a radial basis function-based interpolation of these attributes, which we denote using a capital theta. This is effectively a weighted average, where we weigh our attributes by their corresponding radial basis functions. To give you some more geometric intuition for how this works, let's assume we have three particles, a red particle, a blue particle, and a green particle. Now I'm going to rotate our one-dimensional view clockwise, which will help me better illustrate the individual contributions of particles to the final blended color. As particles overlap, we weight and add their colors together and divide by the total RBF sum. When red, green, and blue all equally combine, then this produces a gray color. Blue and green mix to produce turquoise, red and green produce yellow, blue and red produce magenta, and so on. Note that color here is just one possible attribute. With this modified formulation of radial basis functions, our particle volumes achieve a similar degree of expression as their regular grid and finite element counterparts. But then we can also incorporate their flexibility of motion to interactively explore time series data. However, adding up every last particle for every query point is prohibitively expensive, and so we need to do something smarter. To optimize field reconstruction, we can limit a particle's influence to stay within its radius, and only consider particles within range of our query point. But then that raises the question, how do we get GPU-accelerated range queries? One approach is to use a linearly indexed grid data structure, where cells keep a list of all particles touching them. This works well for uniform particle distributions. However, when particles move and become non-uniformly distributed, these indexed grids fail to cull away particles where features of interest are. So instead, we can use a bounding volume hierarchy. These hierarchies decompose our particles into a tree of nodes. With these trees, we can do a depth-first traversal, culling away nodes and particles that are out of range, and only adding up the particles that actually affect our query point. These trees work much better for non-uniform distributions, and on modern GPU architectures, we can accelerate this traversal process using ray tracing cores. To hide or reveal particles, we recommend resizing them over modifying their weights, then using tree refitting to update their hierarchy. This improves our query performance because ray tracing cores can cull away more particles. Low-weighted particles retain their size, which means that they're still hit and processed, even though their contributions are lower. Note that this does result in a slightly different appearance when viewed up close, because smaller particles appear more dense than low-weighted particles. But from a distance, the effect is less noticeable, and overall the performance improvements seem to be worth the trade-off. Then, when particles move, we recommend rebuilding these trees over refitting them. Refitting causes internal nodes to overlap when particles move in different directions, and this overlap slows down our query performance. On the other hand, rebuilding the trees reduces this overlap, and it maintains good query performance. The tree rebuilding is slower than refitting, but both are really easily real-time thanks to GPU acceleration. Finally, for very large datasets, we recommend clustering particles along a Hilbert space-filling curve. This optimizes tree memory footprint by reducing the number of internal nodes. We also discovered that in some cases, this can improve query performance, especially where overall particle overlap is really high. Last but not least, to get high-quality images, we need a way to deal with noise over time. These days, volumetric shadows are usually computed stochastically, but we can't converge these noisy frames while interacting with time. Therefore, we propose to use spatiotemporal blue noise, which improves the structure of single sample per pixel images. This technically results in the same visual error as white noise, but the blue noise is much more visualization friendly. Note that using blue noise requires using stochastic ray marching over woodcock tracking in order to maintain a correlation between the input random numbers and the output random luminance values. With spatiotemporal blue noise, it's much easier to distinguish between features and noise for single sample per pixel images, greatly improving understanding during time series exploration. So that's the method. To evaluate our solution, we measured the performance on 5 different time series particle volumes, all of which were found to easily achieve interactive real-time rendering performance. Our findings show that GPU-accelerated tree construction takes less than a millisecond on almost all datasets, though Boiler did need some clustering for interactive tree construction. We also found that the memory usage between trees and particle datasets were roughly equal at about 8 particles per leaf. We also compared our approach to alternative rendering methods and discovered that each responded to particle overlap differently. With low overlap, our approach performs just as well as an RT-Core accelerated particle splatter with early ray termination. But for datasets with high overlap, we do substantially better. Voxel grids do the best in this regard since they handle overlap a priori, but then particle voxelization takes several seconds, which prevents interactive time and radii manipulation. Finally, we measured the relative speedups from ray tracing cores over a software-based traversal across 3 different RT-Core architectures and found performance improvements were best for units with full tree traversal. This suggests that ray tracing cores reduce the impact of divergent tree traversal on radius range queries. All results for this paper are open source and were implemented using the general purpose ray tracing toolkit. Sample code for this project can be found at the link below, or you can scan this QR code. Anyway, that's all I have for now, but feel free to reach out if you have any questions, and thank you for listening.